Okay, we've been talking about gases and gas laws. And again, as we talked about last time, really, that combined gas law is, again, a pretty good one to know. As we talked about, pretty much if you know the combined gas law here and you know the ideal gas law, you pretty much will be able to solve any type of gas law problem that you need. Remember from this one, you basically will just scratch out whatever is constant, whatever is not given to you in the problem. And what you'll be left with is, again, probably the correct gas law that you need. Obviously, the ideal gas law is an important one as well. Remember, as well as we talked about calculating density in grams per liter and molar mass of gases in grams per mole, that essentially both of those formulas that we saw are really derived from sort of the ideal gas law. So, again, if you don't want to kind of remember those two laws or formulas to calculate density or molar mass, you really could just use the ideal gas law and sort of do a little dimensional analysis, and you'll be able to sort of figure out both of those things. Any questions on the stuff we've been talking about there? All right, then I think the next topic we're going to talk about is gas stoichiometry. And gas stoichiometry works the same way as really regular stoichiometry. So, really, we have our kind of four steps in our stoichiometry process, which is balance the equation, convert to moles, do the mole to mole relationship, which is the stoichiometry part, and then really moles is some other unit. Now, gas stoichiometry is really no different, other than somewhere along the way, you're most likely going to lay up the ideal gas law, PV equals nRT. So, not always, but probably most of the time, you're going to probably use a gas law, and probably most of the time, it's going to be the ideal gas law. Remember though that you also could still have a limiting reagent type of problem that could also occur with gas stoichiometry. So that's not just limited to sort of grams and moles. But where you would use, say, the ideal gas law is one of two places. Here up front in the calculation, you would use it to figure out moles. So most likely you would solve for moles, which would be PV over RT. Probably the other most common place that we sort of use the ideal gas law is at the very end of the problem. So instead of like normal sort of stoichiometry problem where we take the moles and we convert them to grams to figure out, for example, how many grams we produce, a lot of times with gases, we're interested in perhaps how much volume of the gas we collected. So very commonly solving for volume at the end here using the ideal gas law is also a very common sort of calculation. All this sort of middle part there, the sandwich there is going to be the same. It's all stoichiometry in the middle there. But again, somewhere along the way, either at both of those spots, you'll use a gas law, or at least at the end, you'll use a gas law or somewhere in those processes. So let's take a look at one here and see what is the volume of CO2 produced at 37 degrees Celsius, 1 atmosphere, when 5.6 grams of glucose is used up in this reaction. So why don't you take a moment there and see what you come up with. Let me give you some numbers. Carbon 12.01, hydrogen 1.008, and oxygen 16 here. All right, so take a few moments to see what you come up with here. Okay, so let's take a look again here. We're looking for the volume of CO2. That's obviously a gas. We have some other gas information like temperature. We also have a pressure here, which is 1 atmosphere. So again, if we just kind of think about the ideal gas law here for the CO2, we have a temperature, we have a pressure. Remember, we always have R, and we're ultimately looking for volume. So one of the things that we are missing in order to get to the volume is the moles of that gas. And that's really where the other piece of information is going to come from, and that's the stoichiometry part of it. So we're just going to do a regular stoichiometry problem here to begin with, and then at the end, we're going to use the ideal gas law there to find the volume. So we have an equation, it's balanced. The next thing we want to do is convert what they gave us, which was 5.6 grams of C6H12O6 into moles. Again, here, we'll go to periodic table to do that. 6 times 12.01 plus 12 times 1.008 and 6 times 16. It's going to give us 180.2 grams per mole here. By the way, this is just a basic stoichiometry problem, as obviously we're not giving anything about the other reactant there. So just a basic stoichiometry problem here. So we'll do our 5.6 divided by 180.2. Going to go 0.03108 moles of C6H12O6. Remember that we do want to get to CO2, so this is where the stoichiometry part comes into play. And from the equation, we can see that for every 1 mole of our C6H12O6, looks like we get 6 moles of the CO2. So that's what we're going to use here to get into the moles that we need. So 1 mole C6H12O6, 6 moles of CO2. The moles will cancel here, and that will yield us about 0.1865 moles of CO2. That again is the kind of missing piece that we need for the ideal gas law here. Again, we also have R always 0.08206 liters atmosphere Kelvin mole. Remember, though, pretty much if it's a gas law that we're going to be converting into Kelvin here, so we need to do that. So 273 plus 37, that's a 310. And now we have everything we need to solve for volume. Volume will equal nRT divided by P. Putting in our numbers here, 0.1865 moles, our gas constant, our temperature in Kelvin, so everything properly cancels out, and our pressure of 1 atmosphere, I think we got going on there. Moles will cancel, Kelvin will cancel, atmospheres will cancel. Going to leave us liters, which is good since we're looking for a volume here. So 0.1865 times 0.8206 times a 310, going to give us 4.74 liters of CO2 would be produced. That would be, by the way, a theoretical yield of CO2 in volume, right? In liters in this particular case. Any questions on that? So it really is the same sort of stoichiometry steps: balance the equation, convert to moles, a little mole to mole relationship. And here's the big difference in this particular one. We are just going to go into the ideal gas law at the end rather than using molar mass to figure out grams or something like that. Any questions on that there? All right, so let's try another one here, see what you come up with. We got magnesium reacts with hydrochloric acid and hydrogen gas is produced. We want to know what is the volume of hydrogen gas produced at STP if we started with 5 grams of magnesium, 2431, yeah. All right, so let's take a look. We're looking for the volume of the hydrogen gas here. Produced at STP. Remember that STP is standard temperature and pressure, and it does actually represent values. So that's 273 Kelvin for the temperature. The pressure here would be 1 atmosphere. So we do have pressure, we do have a temperature, we do have a volume. So again, if you want to take a ideal gas law approach, we have temperature. Again, we always have R, we have pressure, we're looking for volume. So once again here, we are going to need to do a little bit of stoichiometry to get to the moles of the H2, as the magnesium is really the only other sort of piece of information that's given to us at this point. So We have our balanced equation. We're going to then convert to moles. So we'll take our 5 grams of magnesium, go into the periodic table there, 2431 grams per mole of magnesium will get us 5 divided by 2431, 0.2057 moles of magnesium. Once again, though, we're not interested in magnesium. We are interested in the H2. So that, again, is where the stoichiometry comes into play. And from the equation, we can see for every 1 mole of magnesium, we pretty much get 1 mole of hydrogen. So that should make the math pretty easy. We're going to go 0.2057 moles of magnesium. Again, it's basically a 1-to-1 relationship here. So 1 mole magnesium, 1 mole of hydrogen. I think I could do that without the calculator. 2057 moles of hydrogen. So that again is the missing piece that we need, as again, we always have our. So once again, here, the last step, we're just gonna use the ideal gas law here and solve for volume. Put it in our moles there, 2057.2057. R, which is a constant, 0.08206 liters atmosphere Kelvin mole. As I run into that, let me go to the down and to the right. 273 is our temperature, and we're going to divide it by our pressure here, which is 1 atmosphere. So atmospheres will cancel, Kelvin will cancel, moles will cancel, leaving us liters. And in this particular case here, we will end up with times 273. Looks like 4.61 liters of H2 would be produced, which would be our theoretical yield. First off, any question on that calculation? Now, because this was actually at STP, you could have, if you wanted to, solved it another way, like we talked about, which is, remember that pretty much 1 mole of any gas at STP is 22.414 liters at STP. That means really you could have just took the moles that we got here, and you could have took 0.2057 moles of H2. You could have used that relationship here because we were at STP conditions. The moles will cancel, and you get 4.61 liters of H2. So you could have, if you wanted to, again, use that conversion factor. It demonstrates, like we also talked about, that if you don't even want to worry about this conversion, obviously you could always go into the ideal gas law. So you could always go in the ideal gas law regardless of it's STP or non-STP. It's good to go for any conditions. But a reminder that this conversion is only for STP conditions. So if it's not STP conditions, you definitely should not use that conversion factor. Any questions on gas stoichiometry here? Like I said before, it is possible to still have a limiting reagent type of problem. You would still do it the same way. Figure out the limiting reagent, use the limiting reagent to figure out how many moles of the gas that you would produce. All right, the next thing we're going to talk about is Dalton's law of partial pressures, which sounds very difficult, but it's not too difficult of an idea here. And the idea of partial pressures occurs when we have mixtures of gases. So if we had a container and the only gas molecule there in that container is lucky A, that means the total pressure of that container is basically all from the pressure of gas A that's in there. Now, if we have a container where we have gas A, gas B, gas C, I know my alphabet, that's good. And we got all these gases flying around, the total pressure of that particular container would be the pressure of gas A plus the pressure of gas B plus the pressure of gas C. These are what are referred to as partial pressures because they each partially contribute to the overall pressure of that mixture of gases. How do you calculate the partial pressure? Well, probably 9 times out of 10, maybe not surprisingly enough, you're going to use the ideal gas law. And frankly, you'll solve for P for everybody. So you would do pressure for gas A, you would do pressure for gas B, figure it out, calculate gas C, and figure out it. You obviously would then simply just add up all those partial pressures together. That will give you your total pressure. Now, because all these gas molecules are in the same container, the temperature and volume will be the same for all the gases since they're all in the same container. Now, one of the reasons why we can sort of do individual calculations for each of these gases that are in that container together moving around is we oftentimes will assume ideal conditions and ideal gas conditions. And there's basically one important aspect of what makes something an ideal gas that allows you to do a calculation like this, where even though you got multiple gas molecules flying around in the same container, you could almost do the calculation like they were in there alone. And that is the idea that in ideal situations, different gas molecules pretty much don't interact with one another. So they're not attracted to another gas, they're not repelled by another gas. It is almost like in an ideal situation, you could think of those gases as being in there by themselves, even though there's other gases obviously flying around. And that is why we could use the ideal gas law kind of 3 times separately for each gas, and it will work out okay under ideal conditions. So that's basically what we just talked about there. Now, what happens if you do not have enough information to use the ideal gas law in a partial pressure situation? There's actually another sort of version of a gas law that you could use to allow you to figure it out. And that is, as long as you can get to the moles of all the gases, you can use this gas equation here, which is the partial pressure of gas A is equal to the mole fraction of gas A times the total pressure. If you remember, we saw mole fraction in the last chapter. Mole fraction is the moles of A, for example, divided by the total moles. So if you come across a situation where you can't get the moles of each gas, but maybe you don't know what temperature you're dealing with or pressure, and as long as you have one other piece of information, as long as you have either the total pressure or one of the partial pressures, you will be able to use this equation here on the bottom to basically calculate. So again, that is the partial pressure of whatever gas you're looking at. That is the mole fraction of that gas. And this is the total pressure. So those are 2 very common ways that you could calculate partial pressures. Ideal gas law, or again, if you don't have enough to use the ideal gas law, but do have moles and one pressure information, you could basically use the guy on the bottom. Any questions on that there? All right, so let's take a look at a couple here and see what we come up with. All right, a 5-gram sample of helium is added to 5 grams of neon. They're in a 2.5-liter container at 27 degrees. What is the partial pressures of each gas and the total pressure? So we're looking for the partial pressure of helium, we're looking for the partial pressure of neon, and we're looking for the total pressure here of everybody. Helium is 4.003 and neon is 2018. All right, so take a few moments there and we should get 3 answers here. It's got some helium flying around, it's got some neon. Even though they're together, we could basically assume that they're kind of separate or in there by themselves. So we are going to use our PV equals nRT for both of them separately. Here, the temperature would be the same for both, and because it's a gas law, we know we automatically need to convert that to Kelvin, so might as well just do that. And that's going to give us 300 Kelvin. We also know the volume will be the same for each of them, which would be 2.5 liters. And of course, we have R for everybody as well. So really the only thing that we're really missing for each of these guys is the moles. So might as well calculate that here. So we'll take our 5 grams of not magnesium, helium. It's like magnesium, but not. And we're going to divide it by 4.003 grams per mole from the periodic table. And that's going to get us here 5 divided by 4.003. Looks like 1.249 moles of helium. We'll do the exact same calculation here for neon, 5 grams of neon. Using the molar mass of neon from the periodic table, 2018 grams per mole. Gonna get us 5 divided by 2018, 0.2478 moles of neon. So that's pretty much everything we need. Again, we're just going to solve for P for each of them, and that means we're going to divide volume to the other side. So if we do our pressure here for helium, it will be nRT divided by V. Put it in our moles for helium, 1.249 moles. Our R, 0.08206. And our temperature of 300 Kelvin, all divided by our volume here of 2.5 liters. Again, liters will cancel, Kelvin will cancel, and moles will cancel. It's going to leave us atmospheres as the only unit that's left. It's going to be 1.249 times 0.08206 times the 300 divided by 2.5. Looks like a 12.3 atmospheres here. This is what is referred to as the partial pressure of helium in this case would be 12.3. Any questions on that calculation there? Yeah. Helium and neon, they're both noble gases and they're monoatomic, which means they come as ones, if that's your question. They're not like oxygen gas or hydrogen gas or nitrogen that comes as twos. So all those guys in group A, they just come as ones, if that was your question. Other questions? All right, we're basically just going to repeat the exact same calculation here for neon. The only difference is going to be the moles. So obviously we want to use the moles for neon, and that is 0.2478. Again, everything else in this calculation is going to be exactly the same because they are frankly in the same container. Again, moles will cancel, Kelvin will cancel, liters will cancel, leaving us atmospheres. And for our neon here, we will end up with two 2.44 atmospheres. This will be basically the partial pressure of neon in this mixture. Any questions on that? Now, to get my total pressure, I should do what with those two numbers? Basically just add them together, yeah? So we'll take the partial pressure of helium and we'll add it to the partial pressure here of neon, and it'll give us 14.7 atmospheres, I think, in that particular case, as our total pressure. Any questions on any of those there? By the way, which one is contributing the most pressure here? It is helium. The reason, as we'll talk about here in just a second, helium's doing that is it's lighter versus the heavier neon. So because helium is lighter, it's going to actually be flying around a lot faster. And because it's flying around a lot faster, it's going to cause more collisions and contribute more pressure than the heavier neon that's going to be moving slower and causing less collisions. Any questions on that one there? All right. Another one here. We got a sample of natural gas contains 8.24 moles of methane, 0.421 moles of ethane, and 0.116 moles of propane. If the total pressure of the gas is 1.37, what is the partial pressure of propane? So see what you come up with here. Pressure. Really, the only information we're given are moles, right? And that's the same thing if you're given grams, you can get the moles. And a total pressure. So we really don't have enough information to use the ideal gas law, as we really don't know volumes or temperatures or any of those type of things. So this is where we might want to use that other equation we saw, where the partial pressure is equal to the mole fraction times the total pressure in this case. So here we would want to solve for the mole fraction of propane, which is what we're interested in. And that would be the moles of propane, which is 0.116, divided by the total moles, which is basically 8.24 plus 0.421 plus 0.116 moles, right, to give us our total moles. Remember that the mole fraction is not a percentage, so you do not want to multiply it by 100 at the end. It's basically a decimal. It really is a percentage without the multiplying it by 100 parts in a sense. And that'll give us 0.0324 is our mole fraction. They gave us our total pressure here, so our P total 1.37 atmospheres. So basically, we're just going to pop it in here. C3H8 equals our mole fraction, which basically is telling us it's about 3% this amount of gas and 1.37 atmospheres. So that will get us here times 1.37, give us a partial pressure for our propane of 0.0443. By the way, I think this is 8.777, I think, if we add that all together on the bottom. Now, if you wanted to, you could absolutely do the exact same calculation for everybody else there. So, for example, if we wanted to use, say, methane, which is CH4, we would do our mole fraction for methane, which would be in this case 8.24 divided by 8.77. Which would give us basically a mole fraction of a pretty big one here, about 0.9388. We'll put that in, 0.9388 times our 1.37 atmospheres would give us a partial pressure in this case for methane of 1.29 atmospheres. Obviously, there's a lot more moles of methane in here than the other guys, so more likely more collisions resulting in that. At this point, you could obviously do it for ethane as well, or if you wanted to at this point, you do have two of the three partial pressures, so you could add them together and subtract 1.37 from them and get the third one. So there's a couple ways you can kind of get the third one, just do the same calculation, or add these two together and subtract 1.37 from those numbers, and you'll end up with what the last partial pressure is. Any questions on that one? So again, this is a situation where if you do not have enough information to go into the ideal gas law, but you have either a partial pressure, either a total pressure, and you have enough information to get the moles of all the gases, you could use obviously this gas law right there to figure it out. Any questions on those two types there? Yeah. Now, a third sort of partial pressure situation occurs a lot of times in the laboratory when you collect an actual gas. So a lot of times when you collect gases, we oftentimes will involve water. And a lot of times what we'll do is we'll do sort of like a water displacement. So you'll fill something up with some water. And basically, for example, here, a little potassium chlorate, and you heat this guy up. It's going to give you some potassium chloride and some oxygen gas. And if you wanted to collect the oxygen gas, what you would do is perhaps fill a jar with some water, put it in a whole thing of water. And as you start to heat this thing, it will decompose and the oxygen gas will go through the tube into your jar. And it will start to bubble in some oxygen gas. And as it bubbles in oxygen gas, the water leaves the jar, obviously, in this case. when the reaction's over, you'll have this empty spot up here in your tube or your jar. And that empty spot's really not empty. That has, in this particular example, the oxygen gas that you were interested in, or whatever gas you happen to be collecting at that point. But there is sort of a consequence that occurs when you collect your gas this way. We have water, we have a chemical reaction occurring, probably some heat happening. So what happens when you heat up water? It starts to evaporate. So in addition to the oxygen gas that you would collect in this experiment, you would actually get some free water vapor there for free in this case. Now, the problem with that is you're probably not interested at all in the water vapor. You're really just interested, say, in the oxygen gas, or if you're collecting hydrogen, the hydrogen gas, whatever gas you're collecting. So this creates a partial pressure situation where the total pressure, which is really the atmospheric pressure or the barometer reading, is equal to the pressure of the gas you're collecting plus the vapor pressure of water. And that is what is known as the vapor pressure of water. The vapor pressure of water is typically a value that you could look up in a table. So you could look it up in a table based on the temperature. So a lot of times when we are doing this type of thing, it's really a very simple partial pressure situation. Because you're interested in just the gas you're looking for, you take the total pressure and you subtract the vapor pressure of water you look up on that list. And this will give you what is sometimes referred to by people as the pressure of the dry gas. And that's because you basically subtracted off water's contribution to the pressure, which you weren't interested in. Sometimes people refer to that as like the dry gas pressure. And here is a table similar to one you can find in your book. And like I said, you just look it up based on temperature and you get the vapor pressure of water. So this is really just a correction sort of calculation that you do a lot when you collect gas in this situation. Because again, you're not interested at all in the water part of it. You're really just interested in whatever gas you're correcting. So if we look at an example of this, we have a sample of oxygen gas that's saturated with water vapor at 30 degrees Celsius. The total pressure is 753 torr. The vapor pressure of water at 30 degrees is 31.824 torr. What is the partial pressure of oxygen gas in atmospheres? So this is the situation we just saw basically in that picture. And how do you know in like a textbook problem that this is the situation? Usually there's a couple of words that you see in the problem, and this is one sentence that you see. Your sample is saturated with water vapor. That's a really key hint that you need to subtract off the vapor pressure of water in this situation. The other one is it will mention something like you collected the gas over water. So usually they'll mention something like how the gas was collected, and that usually involves water, which tells you that's pretty much the situation we just talked about. So the total pressure, again, in this situation would be the pressure of the gas plus the vapor pressure of water. In this case, they did give us the vapor pressure of water, so we have that, and we have the total pressure here. So the pressure of our oxygen in this case would be our total pressure minus the vapor pressure of water, and that's going to give us 753 torr minus our 31.824 torr. Again, if it wasn't given to you, you would need to go look up that number in a table. And I think your lab manual has a table in the back of it that has those values as well. That's approximately 721 torr would be the pressure of the oxygen gas, dry, basically. Now, they did want it in atmospheres, which means we do need to divide by 760 to convert it into atmospheres. And if we do that there, we will end up with, looks like 0.949 atmospheres would be, again, our partial pressure of oxygen in this experiment without the water's contribution to the pressure. So this is a third type of sort of partial pressure situation. And again, it happens a lot in the lab, and it's really because it's a consequence of how you collected the gas that you have to sort of subtract off water's contribution. Any questions on that one there? All right, questions on partial pressures. So 3 different ways we talked about here, partial pressures. All right. So let's talk a little bit about the kinetic molecular theory of gases. And a gas is composed of molecules that are separated from each other by great distances. And the molecules can be considered points, which means that they consist of basically no volume themselves. So this is one of the reasons that makes something an ideal gas, is this idea that the volume of the gas molecule itself under normal sort of conditions or ideal conditions is extremely small compared to the volume of the container they're flying around in. So what's more important in those situations is actually the volume of the container. That's why if you look at a lot of problems that we come across, they talk about the volume of the container rather than the volume of the gas itself. And that's one of the things that we assume in an ideal situation. Gas molecules are in constant motion and they frequently collide with one another. These collisions are perfectly elastic, which means they just bounce off of each other. Nothing slows anybody down or anything like that. The third one here is the second thing that makes something an ideal gas, and it's this one here. In an ideal situation, basically, we assume that gas molecules neither are attracted to one another or repulse one another. And that's why, for example, what we just did with our partial pressure problem, where we had different gases in the same container, we could do the calculation like they were in there by themselves because one gas in the container will not affect the other gas. And there will be no sort of attractive forces, no collision forces. As we will see, if there is, for example, an attraction between the gas molecule on the right and the guy on the left, that guy, as he comes towards, say, the wall to collide, would actually feel some pullback from the attractive force from the other gas molecule. And that would affect, obviously, the pressure that might happen in that situation. So, under ideal conditions, we don't worry about any of those sort of attractive forces or repulsion forces. Same thing if they were repulsed by a molecule, it would fly away faster, right? And could cause maybe more collisions to occur than, say, less collisions. So those two things, basically, the volume of the gas molecule is not important, and the no attractions between or repulsion forces between gas molecules are basically the two things that allow us to assume ideal conditions and basically roll with the ideal gas law in most calculations. The last thing here is the average kinetic energy of molecules is proportional to temperature. So as we talked about, if we increase the temperature, we would expect the gas molecules to fly around faster, and obviously vice versa there. If we lower the temperature, they will lose some energy and they will fly around a lot slower. Now, again, some of those relationships that we saw through our gas laws, again, Boyle's law, as pressure goes up, so does the volume goes down. And as the volume goes up, the pressure will go down, sort of that opposite relationship. We talked about Charles' law and Guy-Lussac's law. Again, if we increase the temperature in a rigid container, like in Guy-Lussac's situation, we will expect the pressure to increase. And if we lower the temperature, we will expect the pressure to lower. In a Charles law situation where we could keep it at constant pressure, we get that volume to adjust. So as the volume adjusts upwards as the temperature increases, and that allows for basically the collisions to remain constant. And when we lower the temperature, we basically will lower the volume, and that will also allow the collisions basically to maintain. We also saw with Avogadro's law the relationship between volume and moles. So as one goes up, the other goes down. That's what allowed us in stoichiometry there that we saw that if it is constant pressure and temperature, you could do a volume to volume relationship and like a stoichiometry problem instead of, say, a mole to mole relationship that may allow you not to have to, again, use ideal gas law. And what we just talked about there, in an ideal condition, no attractive forces, repulsion forces. So even though we got multiple gas molecules together, we could treat them as being basically separate. Now, we could also talk about how fast a gas molecule moves, and that is what is sometimes referred to as the root mean square velocity, or RMS. And if we look at this graph here on top, this is for nitrogen at 3 different temperatures. So at like 100 Kelvin, we have a majority of the gas molecules right there, and that is about their speed. When we increase the temperature to 300, we see that the speed gets a little faster. And when we go to about 700, the maximum amount of molecules are right about there. And we see that the speed increases. So if we're looking at the same gas at 3 different temperatures, as you increase the temperature, the gas molecule's speed or velocity will increase with it. And it's obviously vice versa as well. If you lower the temperature, it will slow down. Now, if we look at 3 different gases all at the same temperature, which is what we got going on here, we have chlorine over here, which has a speed of about that. We have nitrogen, which has a speed about that. And we have our friend helium, which is about here. And what we see here is what we kind of saw with our partial pressure problem. Helium, which is the lightest, will actually be flying around the fastest, right? And here, chlorine in this group of 3 is the heaviest, and it will be the slowest sort of molecule basically flying around. You can calculate it, like I said before, using this equation here. That RMS stands for root mean square velocity. So that's what the RMS stands for, root mean square velocity. And the units are typically meters per second is typically the units. That is the square root of 3 times r. Not to confuse things, but the r in this case is actually the 8.314 version of r. That's the energy version actually here of r. T is our temperature in Kelvin, and m is actually the molar mass. And the molar mass here actually has to be in kilograms per mole when you use this guy. Now, we had an equation similar at the very beginning of the semester where we used that R value. And perhaps you will remember that a joule is equal to a kilogram, meter squared, second squared. And because of that relationship, that is why molar mass needs to be in kilograms per mole, not grams per mole, so everything will cancel out correctly. So if you take a look at just the units going on in here, we basically have R, which is joules, which is basically kilograms, meters squared, seconds squared. And again, that is Kelvin and mole. So those are all the units after you take the joules out there for here. We have temperature, which is Kelvin, and we have our molar mass, which needs to be kilograms per mole. The mole will cancel, the kilograms will cancel, the Kelvin, the kilograms will Kelvin, the Kelvin will cancel. That will essentially leave you, when you do this, the square root of meter squared divided by second squared, which ultimately gets you to meters per second. The good news is the number is still 8.314, so it doesn't change, even though joule is equal to all those other units. So it's still the same number. So the main thing you got to watch out for here is temperature in our Kelvin and our molar mass here in our kilograms per gram per mole. Any questions on that there? So why don't we try one here? Let's try the 5 grams of helium and the 5 grams of neon we did in that last problem there, the partial pressure problem at a temperature of 27 degrees Celsius. What is the root mean square velocity in meters per second for each of them? So give it a calculation there. A reminder again, helium is 4.003, and our neon was 2018 in this case here. All right, so let's take a look at this. You really actually didn't need the 5 grams, did you? There we go. There, do that. So you really didn't need that part of that, I think. All right, so let's take a look here at this. So we want to look at helium neon at 27 degrees that we did before. And we're going to use our root mean square velocity, square root of 3RT over the molar mass. So if we do this for helium first, take the square root of 3 times our R, 8.314. Again, remember the joules becomes kilograms, meters squared, seconds squared. So there's still a Kelvin and a mole on the bottom. And our temperature here, we do need to add our 273 to it, which would be 300 Kelvin. And again here, this is why you didn't really need the 5 grams. You just needed the molar mass here. So that is going to give us 0.004003. Again, we need kilograms per mole. So we do need to divide the molar mass by 1,000 there to get it into kilograms. That's going to give us 3 times 8.314 times 300 divided by 0.004003. Again, we're going to take a little square root of that. It's going to get us something like 1,367 meters per second, as our kelvins will cancel, our moles will cancel, our kilograms will cancel. And again, our meter squared, second squared will then become meters per second. Any question on that there? We'll do the same thing here for our neon. And that's going to be our 3RT over the molar mass there of neon. Putting that in there, 3 times our 8.314 kilograms, meter squared, second squared, Kelvin mole, our 300 Kelvin divided by, again, we need to convert this into kilograms per mole. So move the decimal place of 3 places to the left. For everything again to properly cancel out, Kelvin, Kelvin, moles, moles, kilograms, kilogram. Gives us 3 times 8.314 times 300 divided by 0.02018. And also take the square root of it would be good, I suppose. Gets us something like 609, we'll call it, meters per second. So you can see what we saw previously, that the helium was like 12 point something atmospheres and the neon was like 2. That's because you can see here the velocity of those helium molecules versus the neon molecules, they're moving about twice as fast, right? So they're going to cause a lot more collisions that's going to occur in this case. Question on that there. That's roughly, I don't know, is that roughly like 3,000 miles per hour, I guess, the helium, yeah, or something in that ballpark. And obviously, that guy's moving about 15 or 14 or something like that as well. So much, much slower. Any questions on root mean square velocity? Now, another sort of idea here in terms of how gases sort of move around is the idea of gas diffusion. And gas diffusion is the slow mixing, if you will, of our gradual mixing of gas molecules by the virtue of their kinetic properties. That is the rate of gas 1 divided by the rate of gas 2 is equal to the molar mass of gas 2 and the molar mass there of gas number 1. These molar masses here are actually just in regular grams per mole. Again, we don't need to go to kilograms on this particular one. So we got a bottle here of 2 things. We got ammonia and we have some hydrochloric acid. And when they mix, they make this white sort of powder there, our product. And that white product there is the ammonium chloride that they make. And we can see that the ammonium chloride is actually happening much closer to the HCl container. And that is based on what we were just talking about. The molar mass here of NH3 is 17. The molar mass of HCl is 36. NH3 is lighter, which means when it comes out of the bottle, it's moving a lot faster than the dramatically drawn here slow moving HCl that's heavier coming out of the bottle. And that is why the mixing occurs over here closer to the slower moving, obviously, HCl. You could calculate the rate of how fast one gas molecule is moving versus the other. Again, if you know the molar masses of those guys. Another relationship is gas effusion. And gas effusion is the process by which gas under pressure escapes from one compartment to the next. So here you can see there's a small little hole opening. Going to allow those gas molecules on the other side to kind of pop out. And we get kind of a similar relationship here. Rate 1 over rate 2 is equal to T2 over T1. These are time. And again, these are rates here. And these are, again, our molar masses as well of each of these guys in grams per mole. So you could use this equation, a formula as well, to figure out things like the problem on the bottom, which I think we'll do here in just a second, I think. So we'll take a little, before we go on, I did miss a 1, I think, when I was doing this earlier problem there. You know, I got 3 of the 4 numbers. I thought that was pretty good. So this one should have been this right here. I know your calculator wasn't broken, just my looking at my calculator apparently it was broken. So obviously that would change over here our mole fraction, and then we should have ended up with 0.0181, I think was the right one. Sorry about that. I got, like I said, I got like 3 of the 4. That's pretty. All right. So I think the other one was okay because I think this number should be right. So I got, hey, I'm batting like 500. They would pay me millions of dollars in baseball if I had batted 500, right? All right, so make sure you note that change there. Now we'll go back and not try to screw up too much on the rest of the day here today. All right. Where we left off was with gas effusion, and again, this is sort of the process where you have a small opening in a container where gases are separated by that sort of partition. And we can use this formula here to calculate different things. So for example, let's take a look at this question. We want to eventually know what is the formula here for this unknown gas compound. If under the same conditions, methane will basically effuse 3.3 times faster than the compound. So you basically have M1 and R1, and you have M2 and R2. I'm going to go with M2 being my nickel compound here that I don't know. That means M1 is going to be my methane, and it doesn't really matter which one you do as long as you kind of keep them together. I know that R1 is methane, which is basically 3.3 times as fast as R2, right? So that's basically what that says. So we can get the molar mass of methane to help us out here, and that's going to be 12.01 plus 4 times 1.008. And again, hopefully I won't miss anything here. So we'll go 12.01 plus 4 times 1.008. Going to give 16.04 grams per mole. Now we can put it into our equation here. So R1 is 3.3 R2 divided by R2, even though I don't know it. Square root of M2, which is my unknown compound, divided by the molar mass here of my methane. The R2s will cancel. That will essentially give me 3.3 is equal to the square root of M2 divided by 16.04 grams per mole. We're going to square both sides in this case. And when we square both sides, that's going to give us a 10.89 is equal to M2 divided by 16.04. I'm going to multiply that to the other side, and that will give us the molar mass of our unknown compound here of, we'll call it 174.7 grams per mole. So by using the information that we had here in this equation, we're able to figure out the molar mass of our unknown compound. Now, can we figure out what the actual compound might be, or really what the X value there is that's missing? We can. We know that everybody there is 174.7 grams. We know we have one nickel, and if we look at the periodic table for nickel there, we will end up with something for nickel, 5869. So if I subtract 58.69 grams for the one nickel that's there, that's going to leave me 174.7 minus 58.69. 116.01 grams is made up of the CO units, right? That's basically what's in the parentheses. So each of the CO units, which we don't know how many we have of them, is basically 12.01 grams per mole for the carbon and 16 for the oxygen, which gives us 12.01 plus 16, 28.01. So if I take my 116.01 and divide it by 28.01, which is each of those units, that will tell me how many of those CO units I have. And roughly, I have about 4, a little over 4, 4.1. And that would tell me that my compound here is actually this guy right there in this case. Any questions on that? So here we used the formula to figure out the molar mass of our unknown compound. We subtracted for sure what we know is we have one nickel, and all that mass that's left is made up of those carbon and oxygen units. Any questions on that there? All right. So gas diffusion, the gradual mixing, and gas effusion sort of going through the hole there from one side to the next, kind of the same formula for each. The last thing we're going to talk about here in the gas chapter is what are sometimes referred to as non-ideal gases, or some people call it real gases, unlike those fake ones we've been dealing with, which are ideal. So in a real gas situation, which typically occurs at really high pressures and really sort of low temperatures as well, we get a deviation from the ideal situation. So if we take the ideal gas law and solve for n, the ratio of moles is 1, and that is basically ideal situations right there. As we start shooting out pretty big pressures here, remember that normal pressure is 1 atmosphere, so we're talking like 1,000 atmospheres, 400 atmospheres, so those are a very significant amount of pressure. We start to see a lot of deviation from an ideal situation. And that is because in those sort of situations, we do have to take into account the attractive forces and the repulsion forces of gas molecules near each other. Because typically speaking, when we have really high pressures, what happens to the volume? It becomes very small, which means now our gas molecules are pretty much stuck in a very small volume near each other, which means they're bound to spend a lot more time near each other as they're moving around, and they're definitely going to have some interaction that's going to occur, as opposed to ideal conditions where they have a little bit more room to kind of spread out and separate from each other. So when we look at the ideal versus a real gas or a non-ideal gas, real gases do not behave like ideal gases at high pressures or low temperatures. The other factor is low temperatures, which means if we have high pressures in these small volumes, we now have low temperatures, which means my gas molecule is now moving a lot slower, which means it's going to be near the other gas molecules for a lot longer time than it would be in an ideal situation. So the ideal gas law, as we talked about, basically takes into account no attraction or repulsion forces between gas molecules, and also that the gas molecule itself doesn't take up any type of volume. And under real gas conditions of high pressures or low temperatures, you do have to take into account those two sort of interactions, the volume of the gas itself and the interaction of the gas molecule. So because real molecules do take up space, because when you have those really small volumes because of the high pressures, now you have a gas molecule that's in a volume that is very significant. You could think of it like if you had a trash can and you tossed a marble in that trash can. The volume of the marble versus the trash can is not all that much. That's the ideal situation. You take the same trash can and you toss a basketball in there, it's going to take up a much bigger volume, right? So than the little marble that you tossed in there. Now the volume of the basketball is going to be very important versus the volume of the container, where the marble there is not all that important because basically the most of the volume is the container. So under these real gas situations, we do have to take that into account. And we see that for argon in a non-ideal situation. We also start to see some deviation as we get into these high pressures of basically the volume of the gas versus an ideal situation. So, with that being said, there is a correction that is done to the ideal gas law in this situation. And this is what is sometimes referred to as van der Waals constant. And this is van der Waals B constant. And van der Waals has constants for A and B, and they're specific for different gases. So different gases will have different constants depending on the gas that's there. Van der Waals, as we'll talk about in the next chapter, did a lot of work with intermolecular forces, how molecules and molecules interact with each other. And the correction here to the volume done by van der Waals is nRT over P. This is all the ideal gas stuff still the same. Moles times this van der Waals correction for the volume, which is the B correction. Now, in addition to that, as we talked about, real gases will attract one another and also will affect the molar volume of a real gas is smaller than what we see predicted by the ideal gas law. And again, we see some separation here when we talk about pressures. And that is based on the attractive forces that's happening. And at lower temperatures, as I mentioned before, those gas molecules are going to be moving slower. They're just going to be in contact with everybody for a lot longer period of time than they would if they just kind of flew right by in an ideal situation. So van der Waals has a correction for that as well, which is his A correction, and that corrects the pressure. So as I mentioned before, if there are some attractive forces, this gas molecule may be attracted to the guy behind it, it's going to perhaps slow him down from hitting the wall, and that's going to affect the pressure that we see in a real gas situation. So also repulsion can force him into the wall a lot faster as well. So this correction values are incorporated into the ideal gas law and gives you what is sometimes referred to as the van der Waals equation, which is a scary version of the ideal gas law here. And here we have the corrected pressure for those attractive forces. We also have the corrected volume for the volume of the gas under these high pressure, low temperature situations. Everything in here is still the same thing in the ideal gas law. That's pressure and atmosphere. These are volumes and liters. These are moles. These are moles, the gas constant, the temperature. This is our van der Waals constant, which you could find in a table. If you look up the van der Waals constant, like I said before, it is specific for different gases. You'll have different values for A and B. You should also, if you ever look them up, make sure you check units because they may not always be the units that you expect them to be as well. So under non-ideal conditions or real gas conditions, you would use the van der Waals equation. Like I said, you would solve it like the normal ideal gas law. A little bit more math going on most likely in this situation, but you would basically solve it the same way. The reason we use the ideal gas law in most situations, and in most situations we assume ideal situation is, if you go back to this original graph that we saw here, wherever that original graph was, there it is. And if you look at pretty much most of the time of where we're kind of spending our time, we're pretty much at 1 atmosphere, which is in this ballpark. Maybe we're a little bit bigger than 1 atmosphere. And even if you were a little bit outside of that one atmosphere, a little bit more than one atmosphere, you can see that most of those lines are not deviating all that much from ideal situations. And that's why it's useful to use PV equals nRT, because it's a pretty universal gas law that you can use in most conditions, as long as you're not super high pressures or really low temperatures. And you don't have to worry about, okay, what gas am I dealing with, and getting correction values and stuff like that. The van der Waals equation is more of a specific formula that's used under those kind of extreme conditions. And you do have to take into account all the specific gases that you're dealing with. And that's why in most cases we roll with sort of the ideal gas law, because most of the time in most everyday situations, we're somewhere near that one atmosphere in pressure, or just a little bit above or a little bit below. And it's safe to assume ideal conditions. But again, if you find yourself in a high pressure, low temperature situations, then you do need to use the van der Waals equation. Any questions on that there? It's one you should know. It is possible. I'm going to say it's part of the chapter, so it is fair game. Other questions on that? All right, that wraps up chapter